Video, I'm going to be discussing some salt lakes that we can find in Iran and Turkey. And once we study these features, we're going to learn some very interesting things. Now, one of the things we have to consider is the shape of these lakes and how they're elongated, and they lead right into river channels that then lead into the ocean. And you can see this bay here is where the channel dove into the ocean. Now, there's a particular lake right here. This seems like a very unassuming lake, but this is actually a very incredible spot, because if you zoom in here, you will notice a little blur on the seashore. These are actually streamlined stromatolites, and there's a channel called Geodoxia, which was incredibly instrumental in my study of erosion. And this location is what sparked the brain of the owner of this channel. So I'm going to show you these streamlined stromatolites on the lake shoreline. So he grew up in Turkey and he saw these streamlined stromatolites, and he was trying to figure out what sort of features could have made this, or what sort of conditions. And the most prominent theory that came to his mind was a water current to streamline these out. Now, when he went to Canada, from his understanding of Turkey, he was then able to see massive streamlined features in Canada. And this is in the Ontario region of Canada. And so, I mean, I love this channel. It's incredibly mind-boggling, and I've used some of their clips in my documentary. Keep in mind, this rock is covered in glacier polish, right? Or it was polished by water. But either way, with this demonstration, you can see how, fluid dynamics is what's carving this, even down to the subtle turns and all of the little features of the channeling. And you look at this landscape, it's all rutted out. You can then go in and see the streamlines, and you can see the ruts. And he does a great job. I highly recommend the channel Geodoxia. Let's see, there's another spot here that was pretty sick. This is an interesting feature. So how would you explain that feature with ice? Right? It'd be almost impossible. Now, you could say, oh, well, there was massive meltwater discharge or whatever. Sure. But either way, the erosional evidence itself is only saying high-speed water erosion. And that's what you need to take away from studying erosion, is you only look at what is actually being shown. Okay, now let's go back to Turkey. And so we know there's stromatolites here streamlined. We know these lakes are streamlined. And these lakes run right into massive channels. These are valleys that then lead into the ocean. And another great example of this is this spot in Greece, right? This is a nice river channel. It's a nice lake. A lake is a scoured trough, right? And then this right here is a massive double cataract formation, right? So if you go to, Washington, and you see the double cataract formation with the intermediate ridge, just understand this is the exact same feature, except for the ocean did it. Now, both of the double cataract features in Washington are, when you combine them, it's like, 2 miles, 2.3 miles or something. This is 34 miles. So that's just a little perspective for you. And then you can also get, you can see the terrace line right here. So you know exactly the water level was there for a fact. And right here is a plunge pool feature. So water was coming off of this ridge, and you get a streamlined plunge pool. Okay, so then when we go back to Turkey and we find this, and these are streamlined within the channels, Right now we see how these are troughs. They're dug out scours. And then they're filled with, salt water and lots of salt deposits. What is that going to indicate? And all of these accretion ridges here. So we're getting a lot of features of deposition. Now, the evidence has only begun. It's going to take me hours to explain all this to you, but I'm just going to keep going. Right, so you can just go and check out salt pans until you find cool features, but I'll save you the time and go straight to the cool ones. This right here is in Turkey, and you can see that it's somewhat streamlined. You got a channel that comes through here, and then right here you've got a channel as well. And when we follow this channel on the edge, right where you look at the edge of a river, they've got ripples on them. On the edge of this channel, you also have ripple-like features. Now they have been eroded away into mounds and stuff, but nonetheless, these aren't eskers; these are ripples. And let's get a little wavelength check. I mean, it's kind of a messy feature, but we can estimate the. Let's do feet. 320. So that's on the Washington level, Lake Missoula flood type of level. Now when we go here, we kind of see a point where this looks like an expansion bar, and we go to where the water current was focused, and we also find streamlined mounds, right? But of course these look like massive ripples, and that's what I think they are. Now ripples very commonly have U-shapes in them, and these obviously have that U-shape with the trough in the exact same spot you would expect. But these are very thick, and they look like they're actually pretty tall. Let's see how high it is. I'm not really getting a good reading on this, but I'm sure these are like 20 feet thick at least. And then mounds all in there. So that's a cool spot. And then let's look at this like here. Kind of see it went this way. And then this right here is a cool feature, right? Classic plunge pool type of shape. And then the tail, right? So it's a very directional feature. So now we're getting an idea that this is a direction that happened in the time when this was eroded. Then let's take another step later to where the water current decreased, right? And then it comes through this channel. So first, the focusing force of the water focused here to dig this trough here. Once the current decreased, it worked this area here. And erosion works backwards, right? So it started here, and it worked its way backwards. And this is a little over a mile wide. And then take one more step back into the to this river, and then take another step back into the modern river. So that's what's so cool about erosion, is you can look at the stages of it. And terraces give us so much information. And then that river doesn't even really go anywhere. It kind of ends right here, kind of as a lake, really. So that's a cool spot. Let's see, could there be something cool here? Oh boy, what is this? So this is a nice, this feature is something I call fluvial sediment lobes. Some people call them chevrons. Some people call them, what's another name for these? I don't know, but some of these in like North Carolina, when people are studying the Carolina bays, these are all over the rivers up there and across the landscapes, and they think they're all they think they're aeolian sand dunes, which means wind-driven sand dunes. But most of the time, there's strong evidence to prove that they're not. And then we get over here, we find these features. They look like ripples, right, that have been streamlined around. And you get a mound right? So that's a good spot. But actually, let's check out these mounds here. So keep in mind, mounds are actually the world's most widespread geologic mystery. Keep in mind, no geologist is able to solve the mystery of the mounds. Okay? Not because it's a difficult mystery to solve. I mean, I show you this spot and you already know how it formed, right? You can see the river channels. It's not like mounds are a difficult mystery to solve once you get all the data in. But they can't solve it because if they do, well, then you're looking at mounds 13,000 feet in elevation in Ethiopia, and you're saying these were from fluvial features? There's no way. So, yeah, also Colorado, Wyoming, thousands of feet in elevation. So it's not like it's hard to solve that. They just really don't want to. Let's check out here. Let's just look at directionals. We can see this being an intermediate ridge. That's telling us that this is probably a scarp edge, escarpment, right? So we kind of see a directional feature coming across here. And then this is a cool lake, right? This is a very directional lake. This would be the scarp edge, and that would be the tail. And you get some accretion ridges in there. You get some little scoured lakes. And it's all salty. Just put that in your notes. Just write Na+. Now let's check out this lake. What's going on here? What are these? Polka dots? These are little mounds. Okay. Now, from the mounds, then we get drumlins, right? When mounds become more streamlined, they become drumlins. Okay. These ones here look like they're actually made out of rock. But this lake right here, this is Lake Urmia. It's a fantastic location to start figuring things out, right? Parallel ruts, parallel paths of water. Let's go. What the heck is going on? It's almost as if water washed through here. Fantastic. Wonder why these, almost like a ripple formation there. The horizontal forms are most likely ripples. Yeah, so just drumlins this whole area. Some spots show nice curving drumlins, like this here. Right, that shows us exactly how the water current curved. And then the curve of the water current follows the coastline. So it's a water current that carved the coastline. Okay, just like all the other salt lakes I've shown you so far, it's water currents that carve the coastline, and it's their digging power and excavating power that makes the lakes. Now, the reason why water, a fluid, is the absolute best feature to make a lake is because it can dig out sandstone and it can also carry it away. So it digs out the material, breaks it apart, and then it carries it away. Because if you just break it apart but don't carry it away, you're not going to make a lake, right? So if you got an ice sheet that's really powerful, it can't really make these lakes, obviously, because they're filled with salt. And how are you going to get ice making a circular path of drumlins, right? So drumlins have nothing to do with ice. Just put that in your notes as well. And yeah, this spot's just so sick. Look at these. I would love to visit this spot. It'd probably be pretty boring from standing view, but if you were able to fly over it, it'd be fantastic. And you'd also need a low water level to see these features too, I'm sure. You know, after a good year or two of rain. They might get deeper underwater, but it seems very salty. And then we go to this spot here and we see the lakeshore lines, aka terraces. And all of these ravines, right, were obviously made from the water. And then all of these features here also being ravines. Get that nice curving path. All right, let's go to one more spot. Let's go farther over to Iran. This guy here, I like this one. So we got some cool sediment here. Kind of some big features. And then what are these? Are these ripples? Or are they parallel paths of... Yep, see these aren't... They could be ripples, but I think these are parallel paths of parallel ravines. Which indicates sheet water flow, of course. But I know a cool spot here. Let me find it. It's not that. Cool mounds there. Oh, there it is. This is the cool spot. So we've got our little drumlins features, our parallel ruts, aka drumlins. And then they're also in perpendicular to the ripples, right? So parallel paths are perpendicular to ripples. That's just a fact. You can observe that every day of the week. Now let's check the ripple length. Right, so both of these features help verify one another. Oh, almost 1,000 feet in wavelength. So we've got ripples almost 1,000 feet in wavelength. We've got a channel right next to it. Parallel channel, that is. Well, perpendicular to the ripples, which means it's parallel with the current. So that's all making sense. And then we've got more features. So yeah, that's it for this video. Please like and subscribe. I just want to let you guys know about salt lakes and how fascinating they are. So please leave a like and stay tuned for more. And I'm just going to keep trying to find something cool, actually. Salty, salty, salty. What is this? See, it's so easy to find mounds. Just look at that. They are widespread, no doubt about that. Let's see what's over here. So you can see this is a big fluvial deposit. And it kind of washed down this way. Now when you have a deposit this shallow, that can only form completely underwater. Because if it formed above water from a landslide or something, it would need a steeper angle due to physics. And friction and stuff like that in order to facilitate kinetic energy. Yeah, so this landscape is pretty cool. It's all salty. And these, so what's actually popping out here, obviously what makes this landscape so cool is all of these deformed features. These are anticlines. So imagine this got pushed upwards, right? And then it got terraced flat. That cross section leaves the rings. So because all of these anticlines are terraced, that's telling you that there is sheet water flow to terrace them flat, or else they would be more round and uplifted. And these are uplifted features, basically volcanic pipes, but they're actually made of sandstone. They're not made of, of basement rock. These are made of sandstone. So I think these are actually a great evidence for catastrophic plate tectonics. Because how else do you get sandstone turning into pipes that plume upwards and create all of this amazing deformation? And then salt tectonics is also another thing that is kind of like this. You find plumes of salt pushed upwards. How do you get salt to do that? Well, it takes a tremendous amount of force. And if sandstone can do it, sandstone surrounded by sandstone can be uplifted in a volcanic pipe, then the idea of salt tectonics being driven by a slightly different density of salt being just a little bit lighter, I mean, there's no way because of kinetic friction, or static friction rather. But yeah, so keep in mind catastrophic plate tectonics when you find features like this, anticlines that have been planed flat. This one's cool because it's got a little lake around it. All right, that's all. Thank you all. Bye-bye.